So some other things that are conserved, we've got energy. Energy cannot be created or destroyed. Again, it can change form, it can transfer from one object to another, it can go from one kind of energy to another kind of energy, but the total amount of energy must remain the same. This can help us understand how it is that energy is going from one place to another. Now, energy generally takes three overall categories. First, we have kinetic energy. Kinetic energy is the energy of motion. If an object is moving, it has kinetic energy. Second, we have radiative energy. This is energy as light. If you've ever walked into sunshine after being in the shade, whether it's a cold winter day or in the middle of summer, you can feel that difference. That is energy as light, radiative energy hitting you and you absorbing it and getting warmer. Our last type of energy is potential energy. Potential energy is stored up energy or energy from position. So because of how things are positioned, they may store up energy. Now, one way that kind of helped me start to understand what potential means, if you've ever had the "you have so much potential" talk, maybe in junior high or high school. Well, what they mean by "you have so much potential" is that you could be doing really great things, but you're not right now. You could be getting an A in history, but you're not. You have potential. You could be doing the things. This is the same idea for potential energy. This is energy that is there, but it's not doing anything right now. It has been stored up because of the position of objects, but it is not actually in use right now. We'll see a couple of examples of potential energy in a little bit. Now, going back to the idea of kinetic energy. Again, kinetic energy is the energy of motion. One type of kinetic energy that's going to be important for us is thermal energy. Thermal energy is the kinetic energy of the microscopic particles, the energy of motion for all of these tiny things that are making up the overall big thing that we're looking at. Now, what this means is the greater the kinetic energy, the greater the thermal energy. Now, this could happen because the particles are moving faster. Faster particles means greater kinetic energy, therefore greater thermal energy. But the thermal energy is also the total energy, which means we also have to worry about the total number of particles. Now, thermal energy is related to temperature. Hopefully you've learned or heard somewhere previously that temperature has to do with how fast the particles are going. However, temperature is the average speed or the average kinetic energy of all of the particles. And so if we have relatively few particles moving slowly or lots and lots of particles moving slowly, in either case we have the same temperature. However, thermal energy is the total energy of all of the particles, not just the average. So yes, they're absolutely related. Faster motion is going to mean a greater thermal energy and as well as a greater temperature. However, they're not exactly the same. A great example of this is actually cooking. So, for example, if you've ever made cookies before, depending on your recipe, you have to turn on the oven to preheat. A nice standard temperature for preheating the oven is somewhere around 375 degrees Fahrenheit. Notice I'm sticking with Fahrenheit. So you set your oven to 375 degrees Fahrenheit. Then you decide to boil up some pasta for dinner. Well, boiling pasta, boiling water, has a temperature of around 212 degrees Fahrenheit. So which one has a greater temperature? The 375 degree oven or the 212 degree boiling water? The oven has a higher temperature, 375 degrees as compared to 212. Now think of the motion you do when putting cookies into the oven. You open up the oven and then you stick your arms into the oven and then take them back out. As you do that, it is warm. You don't want to hang in there for a long time, but you're not hurt by that motion. Now imagine doing the exact same motion into the boiling water, sticking your hand into the water and back out. By the way, don't actually do this, only imagine it. Do not do this. In this case, if you do that, you will be hurt. You will be damaged. Now, the reason is, although the water has a lower temperature, it has a greater thermal energy. The water is denser and therefore has a lot more particles in it than the hot oven did. And because of that, it can transfer the energy to you a lot faster, and therefore you get burned. Okay, so again, do not actually do this experiment, just think about it. Okay, so there is a difference between temperature and thermal energy. Thermal energy is the total amount of energy of the microscopic particles. Temperature is the average kinetic energy of all of those particles. Now, when dealing with temperature, we have varying scales. Those of us who grew up in the United States, we're most familiar with the Fahrenheit scale. In the Fahrenheit scale, water freezes at 32 degrees Fahrenheit and boils at 212 degrees Fahrenheit. Most of the rest of the world uses the Celsius scale. In Celsius, 0 is water freezing and 100 is water boiling, and we have 100 degrees Celsius between water freezing and water boiling. In astronomy, we actually use a different scale more frequently. It is the Kelvin scale. The Kelvin scale, 1 Kelvin, is actually the same as 1 degree Celsius. However, what's different is our 0 point. The 0 Kelvin is the coldest anything can be. If you've ever heard of absolute zero, that is the point of zero that we use in the Kelvin scale. Absolute zero is the coldest anything can possibly be and is 0 Kelvin. Now notice that there is still 100 Kelvin between water freezing and water boiling. It's just our 0 point that is different. 1 Kelvin is the same as 1 degree Celsius. One type of potential energy that's going to be important for us is gravitational potential energy. This is the energy stored up as two masses are separated. Okay, so think about what gravity wants. Gravity wants all masses to be together. So as we pull them apart, we are giving those objects energy, and we're storing up that energy. Now when we continue to hold them apart, it remains stored. But if we release, then the two objects will be pulled back together due to gravity. We are converting that potential energy into motion, into kinetic energy. Now, gravitational potential energy is determined by two things: the object's mass and the object's distance. So imagine that I accidentally drop my phone onto my foot. It's uncomfortable, I feel it, I notice it, but I'm not really hurt in any way, other than my pride in feeling stupid in front of people. Now imagine I've got a bowling ball, and I accidentally drop a bowling ball on my foot from the same height. In this case, not only do I feel stupid, but I'm probably going to end up in the emergency room. The difference in this case is the amount of mass. A greater mass means a greater potential energy, the ability to do more stuff. Now, the other thing is the distance. Okay, so I have bowling ball, I drop it on my foot, just holding it at regular height, it absolutely hurts, and there's bad times. Now, if I do the same thing, but holding the bowling ball at arm's length above my head, it's going to be even worse. The greater the height, the longer the two objects get pulled together, the greater the acceleration, so the faster they're going to hit into each other. Okay, so the greater the distance is, the greater the potential energy as well. Now, previously, I actually told you a little bit of a lie. Mass is not actually conserved. Now, before I did delve too much into that, in most circumstances that we deal with in our lives, mass is conserved. You don't have to worry about it. However, when we're dealing at very high energy or very small amounts of mass, we actually see that mass by itself is not actually conserved. Instead, mass and energy together become conserved. Hopefully, you've seen this before. E equals mc squared. This is probably the most famous equation ever. E is energy, equals m, mass, and c, the speed of light, squared. This shows us that energy and mass are related. That if an object has greater energy, it has greater mass. If it has less mass, it has less energy. Okay? Energy and mass are related, and in fact, you can actually convert mass into energy and energy into mass. Okay? So again, I lied to you a little bit before, but in most circumstances that we deal with, mass and energy by themselves are conserved. However, in very high energy things, we see that we have to conserve them together. One great example of this is actually a hydrogen bomb. In a hydrogen bomb, this actually uses a nuclear reaction to convert mass into energy. Specifically, a hydrogen bomb converts about 3 ounces of matter into the largest explosions mankind has ever created. These things are incredibly powerful because we're converting straight from mass into energy. Now, understanding this conversion of mass to energy will actually help us understand the very early universe, more particularly how it is that we can convert energy into mass. We'll talk about that later on when we get into studying the universe itself. Also, as we understand this conversion of mass into energy, this will help us understand stars. Our next unit is going to be all about stars, so we're going to have to worry about how it is that we convert mass into energy, producing that energy that fuels the stars.